Hi chemists, this is Mr. Barron. We're going to be talking about states of matter. Oh yeah, the most exciting stuff ever. We're talking about melting, we're talking about freezing, and yes, we may even talk about vaporization. Oh yes. I would pause this video right now, read all the little parts of this slide, and make sure you understand every little component of it. Moving on. One of the big things is that we actually refer to solids and liquids as the condensed phases. Gases behave a little bit different, and that's why they deserve study entirely on their own, and we'll be studying gases right after liquids and solids, which we call the condensed phases. So in terms of the states of matter, the state of substances at a particular temperature temperature and pressure depends on two things: the kinetic energy of the particles, how fast they're moving, and then the strength of the attraction between the particles. We're going to refer to the strength of attraction as intermolecular forces as we move on. Again, I would pause this slide, read everything. All right, phase diagrams. We've talked about phase diagrams, and a phase diagram shows at specific pressures and temperatures what happens to a particular substance. This one is a little bit flipped. It has the pressure and the temperature. I usually like to have temperature on the y-axis and pressure on the x-axis, but in any case, if I have a gas at this particular pressure and temperature, if I want to change it to a liquid, I would need to increase the pressure. Increasing the temperature of this gas would not change it into a liquid. So phase diagrams tell you a lot of information in terms of what state of matter a substance is in. Phase diagrams also differ depending on what substance they are. The phase diagram for liquid water is vastly different than carbon dioxide. Because for liquid water, see how this line, the phase, the interface between solid and liquid is kind of curving back like this, and this one's curving forward. This one for water is one of the main reasons why the ice actually floats on top of the liquid, and we'll get to more of the reason behind why ice floats in just a little bit. So phase diagrams. The AB line we call the liquid vapor interface. It starts at the triple point down here, and that's at the triple point where all three states of matter are in equilibrium, meaning all three states of matter exist at the same time. It ends at the critical point B. Beyond this critical point, above this critical temperature and critical pressure, the liquid and the vapor, you can't really tell the difference between one or the other. We use the word indistinguishable, meaning we can't really tell which one's which at that point. Each point along this line is the boiling point of the substance at that particular temperature. So at this pressure, we could go down, figure out what temperature it boils at. At this pressure, we could figure out what temperature it boils at, and so on and so on. The AD line is the interface between the liquid and solid, and of course that's the melting point at each of the pressures we can find along that line as well. Below A, the substance cannot exist in the liquid state of matter. Along the AC line, the solid and the gas phases are in equilibrium. The sublimation point at each pressure is along this line, so this is where sublimation occurs. So, looking at the phase diagram of carbon dioxide specifically, the low critical temperature and critical pressure for carbon dioxide make supercritical CO2 a good solvent for extracting nonpolar substances such as caffeine. We've talked about this because we can form liquid carbon dioxide. What we can do is it can actually go into the coffee bean and dissolve the nonpolar caffeine, because like dissolves like, and extract it from the coffee. You can just change the pressure and then you lose your carbon dioxide. It changes into a gas. Now we're going to talk about gases specifically formed from liquids. So every liquid evaporates until what we call an equilibrium is reached. So if I have a vacuum where I have no gas above this liquid ethanol, it will evaporate until it fills this space. The amount of pressure it exerts on this other liquid that's in this U-tube is what we call the vapor pressure for that liquid. For vapor pressure, as more molecules escape the liquid, the pressure they exert increases. So an example of this, the vapor pressure for alcohol is higher than for water. This means that alcohol, if I put it on a table, it would evaporate a lot faster than water if all conditions were kept exactly the same. That's because its vapor pressure is higher. The liquid and vapor reach a state of what we call dynamic equilibrium, and what that means as molecules escape into the gas state of matter, some gas molecules are going back and condensing into the liquid state. We can see this through, and in this simulation, let me get water and let me make it a liquid, and let me add a tad of heat. All right, see these water molecules up here? They've escaped into the gas state of matter. what we'll see over time is that this one will come back and others will escape, is that as some of the water molecules escape into the gas phase, some in the gas phase escape into the liquid phase. And overall, the amount of molecules that are liquid and the amount of molecules that are gas stay equal to one another, but that's what we call a dynamic equilibrium because it is constantly changing. You'll see some are coming back and becoming part of the liquid again, and others are bouncing off and being part of the gas. So let's go back to our PowerPoint slide. So how this vapor pressure is affected is dependent upon another thing which we call intermolecular forces. There are forces between atoms and forces between molecules. The forces between two atoms chemically bonding together we call an intramolecular force. That's within a molecule. Then there's intermolecular forces, which are between two separate molecules. As far as intermolecular forces are concerned, the attractions between these molecules are not nearly as strong as the intramolecular attractions that hold the compounds together, meaning this attraction is way weaker than this one. Now, however, they are strong enough to control properties such as boiling, melting points, vapor pressures, which we were just talking about, and something else we call viscosities, which we'll get into more later. The intermolecular forces as a group are referred to as van der Waals forces. So intermolecular forces and van der Waals forces are the same thing. The van der Waals forces is just the more technical name of the group of these forces. So the types of van der Waals forces that actually exist are dipole-dipole, ion-dipole, London dispersion forces, and then last but not least, that's why I faded in at the end here, is hydrogen bonding, which has a very significant role in biological systems. So there are molecules with what we refer to as a permanent dipole. This molecule right here has a dipole because the oxygen is more electronegative, so the electrons are being pulled towards the oxygen and away from the carbon, so the carbon forms a partial positive charge and the oxygen a partial negative charge. That makes it a permanent dipole, and that's due to the electronegativity differences of these two. If you don't remember electronegativity differences, remember that each element pulls on electrons in a different way based on the number of protons and the number of shielding electrons, and we can see here which elements have the largest electronegativity. The further you move to the top right of the periodic table, the more electronegative the atoms. Notice noble gases are not here because we typically refer to them as having zero electronegativity. So dipole-dipole interactions. If I have this molecule next to itself, the partial positive of one end will be attracted to the partial negative of the other. That's a sticky force. Anything that's a sticky force I like to call the intermolecular forces, which also are called, also sometimes confusing, the van der Waals forces. So there is another type of van der Waals force, and it's called the ion-dipole interactions. This type of force involves, say I dissolve a salt and I have a positive sodium ion within my solution, and I have water molecules that have permanent dipoles surrounding it. If I have a single ion by itself and then a molecule that has a dipole, permanent dipole, we would call this an ion-dipole interaction. That again is another intermolecular force. You can think of these intermolecular forces as how sticky the molecules are to one another. The strength of these forces are what make it possible for ionic substances to actually dissolve in polar solvents. We'll talk more about that later. Now there's also another type of van der Waals force called a London force. See these two neon atoms? When they get close together, the protons in the center of the neon atom and the electrons the protons of one neon atom push the electrons, sorry, let me explain it. It's kind of tough. The electrons of one atom push the electrons of the other atom away, which bear this atom's positive charge available for this atom's negative charge. We call this an instantaneous dipole. So sometimes when you have a normal neutral atom that does not have a dipole, the electrons are randomly on one side of the atom. When they're on the same side, they form, at that instant, a polar atom, and that atom now has a slight charge. And if you have two of them next to one another, they can actually stick. That's the same thing as was explained through this kind of goofy animation that I have right here. So when it comes to this type of force, we call this a London dispersion force, and that's why pretty much all atoms, all particles stick to one another in chemistry. This is why whenever we have single atoms, they definitely stick even though they may not be chemically bonding. And it's the attractions between an instantaneous dipole and an induced dipole. We say induced because once the electrons are on one side and the atom looks like this, it can push the other atom's electrons over to it. So moving on. These forces are present in all molecules and compounds, whether they are polar or nonpolar. These forces always exist. The tendency, like how easy it is for the electron cloud to distort like this, we call that polarizability. So permanent versus instantaneous dipoles definitely affect their properties. This one has a permanent dipole. This is the one we've been talking about before, which is formaldehyde. And formaldehyde, its permanent dipole, what's interesting about it is that notice its melting temperature or melting point is negative 92 degrees Celsius. Ethane, however, which has only an instantaneous dipole, meaning that it's only polarizable instantaneously, and it has London forces, and that's how this molecule sticks to other molecules like it. Its melting point is at negative 172 degrees Celsius. So with these two molecules, this one is obviously more sticky because it can't escape into the vapor phase as easy, and that's why its melting point is definitely different than this one. This one is way easier to be in a vapor than this one. Actually, I should refer to the boiling points to understand this, not just the melting points. The boiling point is definitely way higher in this one than this one here. That's why it requires way more energy to change this into a vapor than this one right here. Although normally at standard temperature and pressure, we typically see this thing as a gas. Now, hydrogen bonding. Hydrogen bonding is the last type of intermolecular force we're going to talk about. It's a weak bond between molecules caused by differences in partial charge, meaning the polarity, specifically with hydrogen. This right here, this dashed line, represents a hydrogen bond. Pause it, take a look at it. Now, over here we can see an ice crystal. Ice with water, notice these hexagonal crystals structures that we see here between all these water molecules connecting to one another. This creates the spacing which gives ice a very low density, which allows it to float on top of its liquid state, which is water, liquid water. So ice floats on top of water because of these hydrogen bonds. The dipole-dipole interactions experienced when hydrogen is bonded to nitrogen, oxygen, or fluorine are unusually strong. So as an intermolecular force is concerned, hydrogen bonding is actually pretty strong. And all of these that you see right here on the right are examples of hydrogen bonds. Again, it's dipole-dipole, but it's a very specific type of dipole-dipole. Again, they're called hydrogen bonds. Hydrogen bonding arises because of nitrogen, oxygen, fluorine, NOF. We want to remember NOF here. Those are the elements that play a role in hydrogen bonding, as we've seen from our examples. And then also when hydrogen bonds to one of these very electronegative atoms, the hydrogen nucleus is exposed, which gives it that strong bond. When we look here, you can have hydrogen bonding between a bunch of different hydrogen fluoride molecules. Here's an example of the type of hydrogen bonding that exists with solids versus liquids. Solids noticeably have a more orderly structure. Hydrogen bonding is also responsible for DNA. DNA has that cyclic structure because of the hydrogen bonds bonding the nucleic acids. It's part of the helix, the double helix of DNA. So in terms of the forces, let's skip ahead. The types of forces that we care about are, here we go, this is probably the best slide. London forces, dipole-induced, that's that London force where you have a dipole inducing a charge in another one. Ion-induced dipole, dipole-dipole, hydrogen bonding is an ion dipole. What we want to do is we want to write this down in our notes. So take time, pause the video, and go ahead and get this down. Make sure you understand all of these different types of intermolecular forces and what they're called. Remember, all of these intermolecular forces fall under the category of what we call van der Waals forces. All right, we're going to skip ahead a little bit and move to this one because that last slide was a little redundant. Now we're looking at how intermolecular forces may affect physical properties. The strength of attraction between particles can greatly affect the properties of a substance or a solution. The forces between these molecules is what we call cohesion. They're cohering to one another. Viscosity is a resistance of a liquid to flow. And the greater the intermolecular forces, the greater the viscosity, the slower a liquid will resist flow. It is related to the ease with which molecules can move past one another, and it increases, like I said, with stronger intermolecular forces and decreases with higher temperature. Syrup will flow a lot faster once you heat it up. Think of it that way. Then there's this thing called surface tension. This physical property we can see right here is because of the cohesion that exists between all of the particles in water. Solids. And I'm going to skip through a